Welcome to lecture number 11 for ECE 320 Digital Electronics. Today we're going to talk about transistors. Now, what we've got so far is if I have a piece of silicon, I can build a temperature sensor. If I dope the silicon, I can get N-type silicon or P-type silicon. With that, I can build a resistor. If I take the N-type and P-type connected together, I get a PN junction. That's a diode that has this symbol. A diode is a valve. Only allows current to flow P to N, not N to P. Today we're going to look at another variation. If I take three types, put it together, I get a bipolar junction transistor, and there's actually two types. It could be NPN or a PNP. Now, what transistors do, they're very different than diodes. A transistor can operate in three states: off, active, and saturated. They can be used as a switch to turn a device on and off. They can also be used as an amplifier. And to kind of give a good analogy of what transistors do, this is the Bellagio water park in Las Vegas. What it is you've got a pump trying to pump water up. There's also a valve. The valve controls how much water. The valve is the analogy of the transistor. The valve could be completely closed, turning off the water, like you saw at the start. It can be completely open, allowing the water to flow at max rate. You can also vary the valve and allow only partial flow of the water. And that's kind of what a transistor does. A transistor doesn't produce current. Somebody else has to provide the current. Just like in the water sport, somebody else is providing the water pressure. But then the transistor can't control the water flow. It can turn it off, it can control the water flow, or it can go maximum, like right here. I'm getting maximum flow through this one, partial flow on the rest. So again, that's kind of an analogy what transistors do for you. Pause this puppy. Now, as far as how transistors work, let's consider the NPN transistor. Now, normally there is no current flow, so electrons are negative charge, so this would be the direction of current. Normally there is no current flow collector to emitter. That's because right here I've got a reverse bias diode. If, on the other hand, I go base to emitter, that's a PN junction. That's a diode. I can get current to flow P to N. What happens is, as I have current flowing P to N, I've got holes flowing from the P region into the N region. As holes flow left and right, I've got electrons flowing right to left. For a transistor, the P region is very, very thin, so when the electrons hit the base, they'll shoot right through and wind up over here at the collector. What that does is I can now control the current flow from the current in the base. If the current in the base is 0, the transistor is off. And that's kind of like the video over here. At the start of the video, all the valves are closed, all the transistors are off, there's no water flow. I can, as I increase the base current, I get more and more electron flow. That's kind of like over here. I can control how much current's flowing by the current in the base. Again, I can even make it go high, low. That's the base current controlling the collector current. And eventually there's a maximum. I've got a pump. Somebody's trying to push current through the transistor. Eventually I run out of current. I can max out the current flow. That's when it's fully on. So a transistor is basically a current-controlled current device. The base current is all important. That controls the current through the transistor. In addition to controlling it, I can get amplification. So suppose the doping at the base is something like 10 to the 14th, and the doping on the emitter is 10 to the 16th. For every hole, I have 100 electrons. That's current amplification, 100 to 1. So the symbol for a transistor is this. If I have an NPN transistor, base to emitter is a PN junction. That's this symbol right here. That's a little arrow reminding you there's a diode, base to emitter. That diode is all important. The base current controls the collector current. And actually, since the electron flow is negative, the electrons are flowing up, but then current goes down. I also have the collector and the emitter. If there's current flow in the base, I'll have current flow collector to emitter. If there is no current flow in the base, this is an open. The VI characteristics per transistor looks like this. If there is no base current, then there is no collector current. That's the off state. As the base current increases, I get more and more collector current. In this case, the ratio. 1 milliamp at the base produces 100 milliamps at the collector. 1.2 milliamps at the base produces 120 milliamps at the collector. That's a 100 to 1 ratio. This says that beta is 100. And it depends upon your textbook. Some call it HFE. That's the current. Some textbooks call it beta. The one I was using, I'm using uses beta, but they're the same thing. It's the current gain. The collector current is some gain times the base current. And call it what you want. Beta or HFE. That's the gain of the transistor. That's the active region. And the saturated region, if I have so much base current, well, think of it this way. There's going to be a load line. As I increase the base current, I move along the load line. Up to a point, I can never go past the y-axis, because if we go past the y-axis, the voltage will be negative. Negative voltage and a positive current means the transistor is producing energy, and a piece of silicon can't do that. So physically, I can never go past this point. I can't even quite get to zero. This is the saturated region. If I supply so much base current that I'm trying to go past zero, I'll saturate. I'll max out the collector current and minimize the voltage collector to emitter. I can't go past zero. I can't even quite get to zero. So what we assume is that when you're over here, the voltage collector to emitter is close to zero, but not quite zero, and kind of a number pulled out of the air. We say that when you're saturated, it's about 0.2 volts. So that gives you the three modes: off mode, no current flow; active region. It's a current control current device. IC is beta IB. And saturated, VCE is about 0.2. Now in digital electronics, we tend to use these 2 points. This is the off state for a transistor. So like this is a switch. I'm going to turn off the water, turn off the current. This is the on state. If you have a closed switch, there should be no voltage drop across it for an ideal switch. Transistors aren't quite ideal. It's an electronic switch where I set the voltage to about zero, which almost maximizes the current. That's digital electronics. We operate in these two states. And this region, that's analog electronics. That's where the current is beta IB. As I vary the base current, if I were to do this, then the collector current would also vary, but vary 100 times more. Active region typically is covered in analog electronics. Digital electronics typically just covers these 2 points. So for transistors are kind of annoying. With the diode, I've got 2 states for any given diode. So if a circuit has 5 diodes in it, I've got 32 different possibilities of which diodes are on, which ones are off. One of those 32 is correct. Kind of think about it, if you build a circuit, it will do something. The challenge is trying to figure out which one of the 32 is right. Well, each transistor has 3 states. So if I have a circuit with 5 transistors, I have 5 cubed, 125 different combinations. One of those 125 combinations is going to be correct. The challenge is trying to figure out which one. Well, the states of the transistor, again I mentioned there's off, active, and saturated. The off state is pretty easy to model. The base current is 0, so the collector current is 0. The transistor is just an open circuit. In the active state, I've got a diode, base to emitter. That's modeled with a diode, of course, about a 0.7 volt drop. The current through the base is amplified collector to emitter. That'll be like 100 IB. And again, the transistor doesn't produce current. I need to have somebody over here, some power supply, trying to push current through the transistor. This will control the current. I can turn it off, I can turn it on, I can control it with the base current, but somebody else has to provide the power. And the third state is when you're saturated, the base current is so large that I'm trying to force the voltage collector to emitter negative. It can't go negative, it can't get to zero, can't even quite get to zero. So typically we just say it's something close to zero, like 0.2 volts. So those are the three states of a transistor. And the challenge is, which one is it? Now, it helps to know what the designer's intent was when they designed the transistor circuit. In this class, digital electronics, it'll probably be either off or on. In analog electronics, it's probably in this state. Because if I want to have a sine wave in, if this current's a sine wave, I want the output to be an amplified sine wave. If it's off or on, it'll clip. So kind of a good way to guess is, depending upon what the class you're taking or what the intent was, an amplifier is probably active. A digital circuit is probably either off or on. PNP transistors we don't deal with quite as much in this class. We will see it occasionally, but just for completeness, these are the models for a PNP transistor. Again, this guy right here is a diode. If I don't have enough voltage emitter to base, the diode turns off. If that diode is turned off, all the current is zero. In the active region, I have emitter to base, a diode. That current is amplified by beta, so the current through the base is amplified by beta, typically 100 times. And the way it does it is it dumps voltage. It will dump voltage, collector to emitter, to set the current. It can't dump less than 0 volts. So if I ever try to make the collector to emitter voltage 0 or less than 0, it'll clip at 0. And it can't quite get to 0, it'll clip at something small like 0.2 volts. Close to 0, but not quite 0. In terms of what transistors look like, if you look at the data sheets, these are the two that we typically use in lab. We use this one at 3904 and the 6144. The 3904, the gain is somewhere between 100 and 300. It can handle up to 200 milliamps. The voltage based emitter is 0.7 volts. It's a silicon transistor. There's a silicon diode based emitter. It can handle up to 40 volts. If you apply too much voltage across anything, eventually it will conduct. The 3904 can turn off, on and off, up to 40 volts. More than that, no guaranteed. And it can handle up to 200 millivolt. And when it turns on, it doesn't quite get to 0 volts. It saturates at about 0.2 volts. What we like about them is they're really, really cheap. They're 3 cents each. That's why we use 3904s in this class. The 6144, this is really designed for analog electronics, but it works in digital electronics as well. Its gain is at least 200. It can handle 10 amps. So if I want to drive an 8 ohm speaker at 5 volts, 5 volts at 8 ohms is 625 milliamps. You're going to fry a 3904 if you try to use that. That's why we have this one in your kit. If you want to drive a speaker, use the 6144. It can handle up to 10 amps. Voltage-based emitter is 0.7 volts, can handle up to 50 volts. And when it saturates, it's not quite as good. The voltage is close to 0, but not quite. Its rating is like 360 millivolts when saturated. We don't include quite as many of them because they're like 10 times more expensive, 37 cents each. Another one that we sometimes use are the TIP transistors. This is a Darlington pair. It actually has 2 transistors in it. And so likewise, the voltage based to emitter is 0.7 volts for this diode, plus another 0.7 volts for this diode, gives you 1.4 volts. In addition, when I saturate, I can't get to 0.2 volts. This right here has to be at least 0.7 volts, plus another 0.2 volts across this transistor when it saturates, means the lowest you can get the voltage across it is 0.9. The reason they have a Darlington pair is it's kind of hard to build a transistor that can handle high currents and have high gains. So what they do is they use two transistors. The second one has a high current capability and a gain of like 10. The second one is a higher gain and lower current capability. Put the two together, I have a high overall gain, 1000, and high current capability. But the cost is it loses 1.4 volts across it, and I can't saturate it. A second thing to note, when you look at the package, you can kind of tell what the design is intended for. This is really designed for digital electronics. If you think about the load line, a transistor is going to have a load line typically looking like this. This is the voltage collector to emitter. This is the current collector to emitter. If I operate right here, the power is 0. Power is volts times amps. So here I have 0 power. That's when it's off. When it's on, I have 0 power. I can use this circuit, this transistor, for a switching circuit, digital electronics, because it never dissipates any heat. On the other hand, if I want to operate over here in the active region, I've got a fairly large voltage, fairly large current. This is maximum power dissipation in the transistor. This isn't designed for that. It doesn't have any way to get rid of the heat. As opposed to these two, this has a great big heat sink on it. It's designed to dissipate heat. So this one's really designed for analog electronics. This one's really designed for digital electronics. They'll both use for digital electronics, but if you're taking 321 analog electronics, this is the one you're going to want to use, at least to drive an 8-ohm speaker. So here's a handout. Suppose I had this transistor circuit. Label the regions saturated, active, and off, and determine the current gain. I'll let you pause the video, and then we'll go over that. So picking up the different regions, again, this is off right here. This is saturated, and over here is active. Kind of what happens is if there's no voltage collector to emitter, the current is going to be 0. As I increase the voltage VCE, I get more and more current until the base current is controlling it. At this point, you have IC is your current gain, beta times IB. The current gain is the ratio. 6 milliamps produces 150, 4 milliamps produces 100, 2 milliamps produces 50. It's always a 25 to 1 ratio. So that tells you that beta is 25. And it depends upon the transistor. So let's see how transistors operate. This is kind of the bread and butter circuit that we'll be using. What I have is a 12-volt source trying to push 120 milliamps through that resistor. Your 12 volts at 100 ohms gives you 120 milliamps. Controlling it, I've got the input voltage and 2K resistor at the base. Now to analyze this, we'll draw the load line. We do a lot of load lines in this class. Suppose I'm on the x-axis. On the x-axis, the current is 0. If there's no current flow, I times R equals 0, and VC equals 12 volts. That's this point. On the y-axis, if the voltage is 0, I've got 12 volts across 100 ohms, 120 milliamps. Gives you this point. Connect the two together, I've got the load line. Now suppose Vn equals 0 volts. I've got 0 volts right here. That has 0 current going through the base. Going to need at least 0.7 volts to turn on a diode. 0 milliamps times beta gives you 0. I'm in the off state. I'm right here. Now suppose I took Vn and made this a sine wave. Centered at 0. What's going to happen is the voltage right here goes up and down. When it's above 0.7, I get some current flow. And as I get current flow in the base, IC goes up. And I start moving up this way, up the load line. So what you get is the voltage drops below 12 when I enter the active region. If I do that in Circuit Lab, here's what it looks like. Normally the transistor is off. I have 12 volts across it. When the input voltage is slightly above 0.7, I get current flow, and the voltage at the emitter drops below 12. That's where I've entered the active region. Now this doesn't make a very good amplifier because there's a lot of distortion, but this is what happens on the off point. As long as the input voltage is less than 0.7, there's no current flow, and the transistor is off. Second mode of operation, the active region. This is what we do in 321 analog electronics. In the active region, I apply a voltage, a DC offset for Vn, say 2 volts. The current then at the base is 2 minus 0.7 over 2K. Nominally, I have 650 microamps flowing. Times beta, if beta is 100, gives you 65 milliamps. So this is where I'm trying to operate. Beta IB says I'm on this line, IC equals IB, or IC is beta IB. I have to be on the load line as well. Where they intersect, that's your solution. Now, what happens if I have a DC offset and vary it? What happens is the voltage goes up and down, the current goes up and down. As the current goes up, I move this way, and the voltage drops. As the current goes up, the voltage drops. So what happens is, going to vary the base current right here. If the base current goes up and down, then the voltage, collector to emitter, goes up and down as well. And it's kind of inverted. As the input goes up, the output goes down. As the input goes down, the output goes up. So this is an inverting amplifier. But it's an amplifier. Sine wave in gives you sine wave out. And you can see that in Circuit Lab. If this is your input right here, it's nominally about, it looks like about 3.2 volts. Here's the output voltage. That's your voltage at the collector. Sine wave in gives you sine wave out. That's an amplifier. It's also inverting. That's property of this amplifier. The output has a minus sign in it. As the input goes up, the output goes down. But that's what we do in 321 analog electronics. Sine wave in gives you sine wave out. The third operating point is when you're saturated. What happens is, let's get this out of the way. If the base current is so large, the current that I'm allowing is IC is beta IB. That's the current that I allow, beta IB. The most I can push through this is 120 milliamps. That's your 12 volt power supply, 100 ohm resistor, means it can only do 120 milliamps. Suppose beta IB is equal to, say, 140 milliamps. I'm allowing 140 milliamps to flow, but the circuit only tries to push 120. The smaller of these two wins. So the winner is 120 milliamps. And what happens is I saturate. To get 140 milliamps, VC actually goes negative. I can't go negative because if I did, I would be producing energy, and a piece of silicon can't do that. I can't even quite get to zero. So in that case, I saturate. VCE gets saturated at about 0.2 volts. So with the analysis, what you do is suppose the base voltage right here is 3.5 volts. I can find the base current, 3.5 minus 0.7 over 2K gives you 1.4 milliamps. If beta is 100, I'm allowing 140 milliamps to flow. Then the voltage right here is 12 minus I times R. This becomes minus 2 volts. That's not possible. So what that tells you is my assumption was wrong. I am not in the active region anymore. This doesn't hold. When I saturate, this clips or saturates at 0.2 volts. What I've done is I've moved up the load line. I'm trying to move to right here. I can't do that. Instead, I saturate at about 0.2 volts. When this is 0.2 volts, I can find the current. 12 minus 0.2 over 100 ohms, 118 milliamps. That's called saturation. And Circuit Lab, you can see that. If I take the input voltage and apply a DC offset, if it gets too large, I'm going to saturate the transistor. As the voltage comes down, I enter the active region. As it comes down, I go from here, left, into the active region. The voltage drops. So right here, I'm active. All the rest, when the voltage is clipping, that's saturated. And you kind of see the voltage collector to emitter that's this distance right here. We're assuming it's 0.2 volts. It's close to 0, but not quite 0. So we say 0.2, it'll actually be like 0.1, 0.15, 0.25, somewhere in that ballpark. Now, as I mentioned before, one of the annoying things about transistor circuits is there's a lot of combinations. With diode circuits, there are 2 to the n possible permutations you have to go through to analyze all possible on-off states. With the transistor, there are 3 to the n permutations, where n is the number of transistors. One way to help is if you can guess the right answer, you can kind of find the right answer. It helps to know the answer to find the answer. In digital electronics, usually the transistors are off or on. In analog electronics, usually the transistors are active. But if you don't know anything about the circuit, you're just kind of guessing. So here's the handout again. For this circuit, draw the load line and mark the operating point when Vn is 0 volts, 5 volts, 10 volts, and 15 volts. Let's pause the video, let you do that. Okay, picking up. The load line. When the current is 0, I have 12 volts across the transistor. That's one point of the load line. On the y-axis, when the voltage is 0, I have 12 over 50. That is 240 milliamps. That's right here. 2 points determines a line. Yeah, it's not too bad. Now with Vn equals 0, I have no current flow. I'm at this point right here. That's when Vn equals 0. That's my operating point. VCE is 12 volts, IC is 0. When Vn is 5 volts, this is 5 volts, this is 0.7. Again, that's a diode. Diodes are 0.7 volt drop per silicon diode. I've got 4.3 volts at 1K, gives you 4.3 milliamps. That'd be the operating point right here. 4.3 milliamps at the base produces some current at the collector. When Vn is 10 volts, I have 10 minus 0.7, 9.3 volts at 1K, 9.3 milliamps. So here's 8, here's 10, here's 9, but here's 9.3 milliamps. And the third case is when this is 15 volts. 15 minus 0.7 is 14.3 milliamps. If I extend this, I'm trying to operate right here. I can't have a negative voltage, and I can't quite even get to 0. So in that case, I'm going to saturate. The voltage VC is about 0.2 volts, and then the current is 12 minus 0.2 over 50. So here I'm saturated. Here I'm active. Here I'm active. And here I'm off. So in summary, transistors can either be NPN or PNP devices. They have 3 modes of operation. They can be off, active, or saturated. It results in 3 to the n different circuits to analyze. One of those 3 to the n will be correct, which is kind of annoying. Typically, the transistors will either be off or on in digital electronics. They'll typically be active in analog electronics. And that's lecture number 11 for ECE 320.